talk about some of my work with Kenny Weiss on the topic of generalized winding numbers and specifically how we can use them to improve the efficiency during the deployment of multiphysics codes. So I want to start by putting this in sort of a broader context first. A lot of interesting physics simulation starts with some user-provided geometric object, which is usually defined in terms of its boundary. But before you can actually send that data to an actual code, there's a lot of pre-processing you need to do. And in particular, we're focused on the shaping problem where you need to initialize volume fractions. This process is much more straightforward when the meshes you're dealing with are all conformal, which is why tools like Bezier exist. And so then you can use these to get your volume fractions right away and send them to your physics code like Marble. But all of this is nice, but you can't always have a conformal mesh, nor do you necessarily want to 100% of the time. In cases like this, you have some mesh elements that are only partially occupied by a given material, and you need to sort of compute by hand what the resulting volume fractions should be in that cell. I'm simplifying this a lot, of course, but this is at least the general framework that we're going to be working with. And it is also, of course, worth mentioning that MFEM pops up at basically every step in this pipeline, although the general math that I'm going to be talking about today is fairly general. To go one level deeper into this, the clay component of Axum is a tool to really just simplify this shaping process for both users and developers. Axum itself is another Radius project that's designed to provide a lot of streamlined infrastructure tools that can be shared across all sorts of different multiphysics codes. And the pipeline here works with some user-defined geometric or user-defined mesh along with a set of replacement rules that defines how the different objects kind of interact with each other. This provides users a lot of flexibility in the sorts of objects that they can define and how they overlap, but it requires that sort of the core of that shaping algorithm, the actual computation of the overlap between your geometric objects and your mesh elements be fairly flexible to all sorts of different kinds of input geometry. And so that's what we're focusing on here. To dive into the technical details of shaping, there's a lot of different ways you can compute these areas of intersection. For example, if your shapes are reasonably tractable, there's a lot you can do analytically to compute the actual overlay of these things. But it's not likely that you can do this for every kind of shape that you're interested in. And so a more sort of flexible approach in some sense is a sampling based strategy where you instead just have quadrature nodes, and at each of these points, you just need to tell whether that particular point in your mesh element is covered by your material. And so in this sense, all you need for a given geometric or a given type of geometry is a containment query that tells you whether or not a given point is inside or outside of your shape. Now, close again. Okay, if it doesn't work, I'll just hold the laptop.
the connection. Yeah.
Okay, so in a lot of ways, I said that it's more flexible to define these containment queries than it is to have some analytic implicit representation, but that doesn't necessarily mean it's trivial. I mean, sure, if your shapes are simple, like circles and squares, the process is basically the same. But as soon as you start dealing with more general curvilinear types of elements, that process becomes much more complicated, and typically the methods to do this have to be iterative in order for you to process those kinds of geometries accurately. But at the same time, there is a sort of separate but just as impactful issue dealing with watertightness, which is when you have a shape that doesn't technically rigorously have a volumetric interior to actually query. And it sounds kind of counterintuitive, but it happens all of the time in practical application because all it takes is for a single pair of edges to not connect perfectly like they should, and it can cause your otherwise, fairly expensive and complex shaping procedure to just crash, sometimes just completely unexpectedly. There's a number of reasons why that could be the case, but a lot of them have to do with the sort of mathematical principles that we often define containment queries from. If you have any familiarity with containments at all, you might know about the idea of raycasting. It's a pretty simple procedure where you take the point you're interested in, extend a ray out to infinity, and just count the number of times that it intersects. If it intersects an odd number of times, that means you're inside. Even means you're outside. It's actually very elegant and is sort of well studied in some sense, but you can imagine that it has issues with watertightness, where if you have any kind of gap in your shape and your cast ray just happens to go through that gap, then not only will you get the wrong answer, but in some sense you'll get as wrong of an answer as possible. A point should be inside and you say it's outside. And perhaps even more troubling, there's no real way to tell ahead of time if that has occurred. And so what we want to do is find a way to sort of address this issue. This is more or less how a lot of the existing routines in Axum work, at least, but usually they do so in a way that's accelerated with like a spatial index so that you can classify entire regions of space as inside or outside. That means you only need to actually look at your geometry when you know that you're somewhat close to it, which is pretty great for performance. I will also say that a lot of these methods sort of are only built to handle linear types of objects. So if you pass this thing any kind of curve, more likely than not, it's going to have to decompose it into some sort of approximation, which makes it more sort of numerically tractable, but also you lose some geometric features. And so in whatever algorithm we come up with, we want to really ensure that we're handling curve geometry in a way that sort of maintains that high order geometric fidelity. Now, there is, of course, another way to compute containment queries, those being the eponymous winding numbers. In their simple watertight form, these things just count the number of times that a curve wraps around the point of interest. And if your shape is watertight, the containment decision you get from a method like this is actually the same as you would from raycasting. But it has the really distinct advantage of being able to be generalized to cases where your shape isn't watertight. You just count the number of partial revolutions instead. Sure, the number you get isn't necessarily going to be a discrete integer anymore, but if it's close enough to 1, you can more or less just assume that it is. If you get a generalized winding number that's close to 1, like it is in this case, then you can sort of just take it to be 1 and say that that point is interior. And now this sort of gives us a solution to this shaping issue where you can just replace your indicator function with some containment query that is in some sense derived from your generalized winding number, and then just sort of proceed as you would otherwise. It's the sort of algorithm where if we've designed it correctly, it's almost like we didn't do anything at all, because we're specifically just trying to make sure that shaping isn't interrupted by these, otherwise small and insignificant geometric errors. But we still have to sort of solve this thing because it's not necessarily a trivial problem. Winding numbers themselves have a formulation kind of complex analysis in 2D, where you have this really nice integral formula that is not especially illustrative of how to evaluate it. In 3D, that integral becomes a surface integral to find the solid angles of the surface, but the important details are the same between 2D and 3D. Namely, that if you try and compute these things directly using numerical quadrature, it is challenging. Particularly because no matter how high order your quadrature rule is, you will always get a lot of inaccuracy, and you get pretty bad ones too. For example, anywhere you see yellow on this plot is a winding number that has been computed on the order of like 300, which for a shape like this should only ever be between -1/2 and +1/2. So, that's largely unacceptable. Here's what that looks like when you try and actually do that on a shape. This is like a sort of non-manifold curve thing, which for the record is handled pretty poorly by raycasting regardless. But you can see that using that quadrature directly, you get some points that have, wildly inaccurate results. And you can sort of tell ahead of time that if the number you get is like 800, that's incorrect. But if you get a number like 1 or 2, it's not exactly clear whether or not you computed it correctly. And so it's not exactly ideal to just directly compute these things with quadrature. But the fact that the formulas are built on integrals does mean one nice thing, which is that we can always split up the value of our winding number along the different sections of its domain, which in this case is just the curve itself. So what that means is we only ever have to compute the winding number for individual curves one at a time, and you can just add those numbers together without sort of any reference to how they were originally arranged in the shape. In this case, we're sort of targeting rational parametric curves like Bezier curves and NURBS curves, but a lot of this will hold even for more general kinds of lines, which is sort of an advantage. So this is also where we are going to sort of get a way to compute these generalized winding numbers without doing any numerical quadrature. And that has to do with the simple fact that in 2D, you can always close any individual curve with a single straight line that connects its endpoints. And very fortunately, you can actually derive ways to compute the winding numbers of both the original curve, of the original curve that is closed, as well as the straight line that closes it, both exactly without doing any numerical integration at all. All you need to do is compute the one value, subtract out the contribution of that closure, and then you have your generalized winding number. You just add it to the rest of your curves and you have your containment decision. Now, I want to talk about how we actually do this numerically, and I'm going to start with the easier of the two calculations, which is the winding number for this straight line. We can actually get this from that same formula from before. This time I've written it in Cartesian coordinates, so you can see a little more clearly how that sort of non-singular or near singular behavior starts to mess with our numerical quadrature schemes. As long as our point is approaching the curve, solving this thing directly becomes problematic, with one sort of major exception, being that if the curve you're dealing with is a single straight line, then the angle subtended by that single straight line is actually very easy to compute. It ultimately comes down to evaluating a single arc cosine, which we can do exactly and stably for basically any point in space, regardless of how close it is to the curve. In a lot of ways, I think the more interesting subproblem is the one in the middle here, where we have to compute the winding number for the closed shape. Now, because we have specifically closed it, we can actually guarantee that this one is watertight. And so that means that all of its winding numbers are going to be integer valued. And in some sense, all we have to do is just pick out, well, which integer is it? There's a lot of ways that you can do this, but we sort of came up with our own way of doing this built on generalized winding numbers. I'm going to gloss over some of the technical detail. You can read our paper if you want. But the big idea is that the easiest integer winding number you can compute is actually the number 0, of course, right? And that happens whenever your point is sufficiently far away from your curve. And that's fairly easy to check. All you have to do is put like a bounding box on your shape, be it axis aligned or oriented. And as long as you're outside that shape, you know that your integer winding number is 0. If that's not the case, you can just bisect the curve and try again on each half. And a lot of times in cases like this, especially when you're dealing with NURBS type shapes, it's easier to look at not the bounding box, but actually polygons defined by the control points of these, since they're generally tighter shapes and fairly easy to check for containment. So you just sort of do this down the curve until you have found a bunch of shapes that your point is outside of their bounding geometry. When you're done, you have this polygon that actually provably has the same integer winding number at the point you're interested in as that original closed curve. So you just report that back and you're done. What's I think really nice about this method is that because we are at no point actually casting any rays or computing any intersections between rays and curves, there are, I think, a fair amount of advantages to using a method like this, even in the case of when you know that your geometry is watertight. So as a sort of example of that, here is a SVG file made up of a couple hundred cubic Bezier curves. And what I've done here is I have sort of removed one of these edges. So all of a sudden, just with that simple change, this thing does not have a volumetric interior anymore. And that sort of, poor behavior is reflected when you try and do ray casting on a shape like this. You can see that not only is the result wrong, but it's also wrong in places where we wouldn't really expect it to be, like in places way on the other side of the domain where the containment decision should be obvious. On the other hand, if you look at the same shape with the field of generalized winding numbers, you can see that it is far more tolerant of that same gap in the shape. For faraway points, it basically has no influence on the ultimate containment decision that we make. And what's really interesting is that even for points that are very close to that geometric error, we can actually just round this field to the nearest integer, and it's almost as if we've sort of closed that shape implicitly without actually having to do any sort of extra work on it, which is fairly nice. But in a lot of ways, I think this example is a little more exaggerated than the ones that we sort of assume would be typical in a shaping application. What I have here is an example that looks fine, but if you sort of zoom in on it, you can see that I have mischievously perturbed all of the vertices so that none of them are actually connected to each other. This thing has no interior to speak of, but the field of generalized winding numbers is still fairly well defined. I'll also say here that we are specifically not trying to repair that original surface. That's like a separate, equally more difficult challenge. Really, we're just trying to define a containment query that is more tolerant to the kinds of geometric issues that already exists in these kinds of shapes, and just make it so that those geometric errors don't just like balloon into huge issues during the whole shaping pipeline. So if you're interested in playing around with winding numbers yourselves, Kenny has actually put together a really fun script in Axum that you can use to take whatever SVG file you have on hand, turn it into an MFEM NURBS mesh, and then query that winding number field over a grid of points. And just for fun, I can show you the same shape with more of the curves deleted. And you can see that this fractional winding number field actually does kind of recover what we would sort of expect for points that are inside. If we round that, you can see that, even in a pretty exaggerated example like this, it really does a remarkable job at sort of closing those gaps implicitly. Particularly in the 2D case, I think that these methods are really straightforward to just like put in as a drop-in replacement for existing containment queries, particularly as we start to move our own implementation to one that's more HPC aligned. But unfortunately, real physical space is more complicated than 2D geometry, and this is arguably even worse of a problem in 3D. What I have here is a shape. It's the first example of the Utah teapot that I could find online, and it has all of these characteristic issues. The top is completely disconnected from the body of the tea kettle, and the handle and spout are just sort of haphazardly embedded in the side. These are very common issues because the people who make these models are not always concerned with these mathematical properties of watertightness. And so what we had to do was do the same sort of thing we did in 2D for these 3D shapes. It's difficult, but we actually have some pretty good ideas that I'll share. Can't get away with the exact same procedure because it turns out that even though the basic principles still apply of closing your surface and then computing the winding number of the closed surface and the closure, computing the winding number of that closure is basically just as difficult as it is for that original one, particularly because only polygons have that nice direct formula that we could come up with for line segments in 2D. And there's just not really any shapes of practical interest that we can close with just polygons. With one major exception being if the model you're working with is already sort of tessellated into a SDL model, you can actually just use a lot of these direct formulas right away without having to suffer any inaccuracies from quadrature, which is nice. So in particular, if you have a CAD shape that can sort of handle that discretization process into an SDL mesh, then you might be able to use some of these things. But even in 3D, our goal specifically is to make containment queries that still maintain exact curved geometric accuracy. So unfortunately for us, this sort of discretization isn't really an option for the algorithms that we have in mind. That means that we're going to have to do some kind of quadrature. And really now the goal is to make sure that whatever quadrature we do is not only accurate, but also provably accurate. The first thing that you can do to approach this problem is use Stokes' theorem, since it will turn that 2D tensor product quadrature that you'd have to do on the surface into a 1D integral along the boundary, which right away improves sort of your computational efficiency by like a factor of square root, which is nice, but not exactly efficiency that we get for free. This is sort of a subtle point, but for Stokes' theorem to hold, we need both our original function and the function that it is the curl of, which is the one that we're going to be integrating along the boundary, to both be continuous on that original surface. This is sort of straightforward to maintain for that original integral over the surface, since the only problem is when your query point is directly on the surface, which is problematic for a host of reasons. But this 1D line integral that we're evaluating over the boundary has its own set of problems. Namely, that by constructing it, it necessarily comes with more singularities than the original one. In particular, it has in this form has an entire line of singularities that if that line intersects the surface, then you can no longer use it for this problem. It's sort of awkward to have some points that work totally fine with this new improved Stokes formulation and you get your accurate results more efficiently, but other ones that just don't in a way that's not really a numerical artifact. It's just we didn't meet the conditions of the problem and we'll get the wrong answer if we try. But there is an advantage to this, namely that this particular form of the integrand was a little bit arbitrary, sort of like how you can pick a different plus c when you're doing a 1D antiderivative. And in fact, you can pick different ones that each come with a different line of singularities that potentially don't intersect the surface in the same way. So even though we can't use this blue integrand for this point, we can use this green one and just sort of proceed with that. Now, of course, it is entirely possible for there to be some points and some surfaces that no line of singularities doesn't intersect the surface, but we actually have a pretty neat workaround for this. Like I said, there's a problem whenever that line of singularities intersects the surface, but that surface doesn't have to be contiguous. You could just cut out, you could imagine a small disk that's cut out from that surface to sort of avoid that intersection. And in fact, as that disk shrinks in size to epsilon 0, you can actually sort of account for its contribution to that calculation analytically. In particular, the contribution of that disk is 0. And when you try and do Stokes' theorem on that now punctured surface, you can compute the contribution of that cutout disk, the boundary of that cutout disk on the surface analytically as well. There's a lot of, I think, interesting mathematical details and implementation details that go into it, but this is sort of the big idea, is you can take your point that you otherwise are not allowed to do Stokes' theorem on and just use it anyway, as long as you sort of correct your mistake afterwards. Now, regardless of sort of how many of those 1D line integrals we have to do along the boundary, they're still tricky to solve. And in a lot of ways, I think the way that we do this is a little bit tacky. What we do to make sure that our results are accurate is we just split up the curve into two sections and make sure that the integral along each half is equal to the integral along the sum. It definitely works to make sure that our results are sort of provably accurate, the sort of geometric recursive algorithm. But you know, I think it could be improved a little bit. Now, before I go into the results, I want to say that we have worked out the mathematical details for this for just about any sort of parametric surface you could want to apply it to. But the implementation we have in Axum right now is still fairly restricted to just untrimmed Bezier patches, even though trimmed NURBS patches is definitely in the future. So I'm excited for that. So I hope for now we can just look at some results on these rectangular patches. What I have here is a sphere constructed of 6 Bezier patches with one of them being clipped so that there's like a ring cut out. This thing has no volumetric interior, but nevertheless, we're able to compute the field of generalized winding numbers for this thing without really any difficulty. The fact that it's not closed didn't even come up in the solution. And if we want to actually recover that rigorous definition of containment, all we have to do is round this field. And you can see that we have functionally closed those gaps in our shape. Again, I want to point out here that if you were to zoom in on those places where rounding has implicitly defined this boundary, you would see that it's not actually a reconstruction of that surface. It actually is a little caved in with negative curvature. But just again, I like to emphasize that our goal is not to reconstruct any surfaces implicitly or explicitly. We're just trying to make these algorithms more tolerant to regular shapes that people already use and just sort of carry on with the actual important physics that we want to do. I want to now conclude here with a slightly more complicated 3D example. This one is a planar Bezier curve that I've rotated around the z-axis. And since I did this one by hand, I obviously did a perfect job. And you can see that the shape is totally watertight, indicated by the fact that these slices of the winding number field are all integer valued. But just to make things fun, let's make it non-watertight. And you can see that this ring I've added sort of haphazardly around the circumference here doesn't actually connect like it should. You know, trying to match the edges of one surface to the surface of a second surface is difficult to do by hand or even with a computer. But nevertheless, we can round this field of winding numbers and we can sort of recover what our original intentions were in putting this shape together. Really, that's why I see a lot of this work as really like a productivity kind of tool, since it prevents you from having to go through this typically manual and very precise surface repair when you're actually constructing these shapes, and you can just sort of get on with your simulations. That's what I've got. I'd be happy to take questions. I love talking about this.